Okay, good morning, happy Friday. All right, so we kind of left on a cliffhanger. I know. Last day, what did we, oh yeah, so kind of nice, no quiz this week. We didn't really cover that much or enough to kind of quiz on. And then I haven't heard anything from anyone else, so I guess having the quizzes kind of open during the week seems to work. So I'll work out the kinks over the weekend and just kind of get it set up and let you guys know. All right, so we were working on example 4, right? And so just let's do a little bit of review. It was just last day, but right, we were looking at, well, we talked about continuity, right? So a function is continuous if it's depending on the limits, right? So if the limits exist and the function exists and the limit and the function are the same, right? So if the limit as x goes to a of a function exists and is the same as f of a, right? So it's the same as the function at that point. We say that this function is continuous at a. The function is continuous at a. At x equals a. Okay. And so we looked at some continuity problems, but we kind of skipped a couple because continuity is going to come up later anyways, and so we'll come back to it as needed. But then we started talking about limits at infinity, right? So letting x go to infinity. And so we talked about limits at infinity. Limits as x is going to plus minus, I don't know why I did a square root there. Square roots on the brain. One trick to deal with these, right, is that we leverage, we use the fact that the limit, and let me just pull it up so I have it the same, the limit as x goes to, I'm gonna cheat a little bit and do plus minus, so I'm not gonna write it out twice. I'm just gonna do plus minus infinity, a little bit improper, of 1 over x to the r, right? We use that fact that 1 over x, the limit as x goes to infinity of 1 over x to the power of anything is gonna go to 0, right? And then what we did was we said, okay, well, one thing that we can do, one kind of tool that we have in our toolkit for limits at infinity is that we divide by the highest power of x in the denominator, right? And then we simplify things, and then what we saw was things start to go to 0 and 0 out, and then we're just left with a horizontal asymptote, right? If the limit as x goes to plus minus infinity of f of x equals some value L, right? We say L is a horizontal asymptote. And of course, there are functions that don't have any horizontal asymptotes, and that's fine. But if we're able to arrive at some limit, then we say that that's a horizontal asymptote. So to find limits as x goes to as x goes to plus minus infinity, we divide the numerator and denominator by the highest power of x in the denominator. It's wordy, but when you do it, it's like, oh, okay, that's fine. As long as you're picking from the denominator, right? So that's the only kind of hiccup that I've seen along the way, but otherwise, we have that carrot of everything going to 0 or stuff going to 0. So usually it's 6. So to find limits as x goes to infinity, we divide the numerator and denominator by the highest power of x, in the denominator. Right, kind of wordy, but that's what it is. Okay, so kind of a lot of concepts that we went through last day. Let's keep going with that example 4, I think it is. Example, 4 continued. All right, so let's just have a look back here. So we said, okay, well, we've got this kind of weird situation of having the root in the numerator. And so what we do is we say, okay, well, x is our highest power of x in the denominator, right? So we're still going to be able to apply that rule where, okay, we can simplify things by dividing by the highest power of x. But in order to simplify things, what we said was, well, I need to bring that x under the square root. So then it becomes important, well, is x positive, right? Is it going to positive infinity? Great. Then 1 over x, I can just rewrite as the square root of 1 over x squared, right? The pickle, we said, was, and then so things just kind of start falling out, and that's what's so, I dare say, fun about limits at infinity, is that things kind of just go to 0, and then you're left with just a value for the limit, right? And then we said, okay, I said, go try it out as you go to negative infinity, right? And so that's where we're going to pick up. So I'll just summarize here. Last day we found that the limit as x goes to positive infinity of, and I'll just copy it out here, the root of 2x squared plus 1 over 3x minus 5 was the root 2 over 3. Instead of flipping back and forth, which means that we have a horizontal asymptote at root 2 over 3 as x goes to positive infinity. Right? And so here, this is the horizontal asymptote as x goes to positive infinity. Right? So now we're going to check as x goes to negative infinity. Now find the limit as x goes to negative infinity of this thing, root 2x squared plus 1 over 3x minus 5. So we still divide by x, right? So divide both the numerator and the denominator by x, right? And so what we say is this becomes, I'll write it out kind of lofty here. The root of 2x squared plus 1 over x divided by 3x minus 5 over x. And then I'll write a little note here. We still divide by the highest power of x from the denominator. I combine the two. The denominator. And then we divide by the highest power of x to the denominator, which is the combination of the numerator and the denominator. Words. Okay, oh well, it's Friday, right? So don't need to talk for that much longer. So we still divide by the highest power of x by the highest power of x from the now I've made it a word, denominator, from the denominator, okay, but we need to be really careful because now x is going to be negative, right? It's going to negative infinity. But now we need to be careful because x is going to negative infinity. So x is now negative. So x is now negative, right? And so what we did earlier was we said, okay, well, to bring this x underneath this, oh, sorry, it's lagging. To bring this x underneath the square root, right, then I can just square it and put it under the square root, okay? If I square a negative number, then I lose that negativity, right? And so, so we need to preserve that negative, yeah, the negative, period. Okay, so, recall that 1 over, oh, sorry, no, the square root of x squared, let's just start at the beginning here, right? Because I want to bring that x under the square root, which, okay, we know we have to take the square and then the square root kind of undoes it, right? And so, but the square root of the x squared is actually going to be, so technically it's the absolute value of x, which is fine, right? If x is positive, right? So by definition, the absolute value of x is a piecewise defined function where it's going to be x if x is greater than or equal to 0, right? But it's actually negative x if x is less than 0, right? So here, this is the one that this is the situation that we have since x is going to negative infinity. Since x is going to negative infinity. Yeah. So what happens is that therefore, when we do 1 over x, right, and I bring it under the square root, it actually becomes the negative square root of 1 over x squared, right, to preserve that negative. So we need to preserve the negative. Okay. Other than that, everything's hunky-dory. We go ahead and just work the limit just like we did earlier. So now I know that in order to bring, sorry, it's lagging. In order to bring this x under the square root, all I need to do is put a negative out front here, and then it'll work the way I want it to. So I'll pick up this kind of down here somewhere. Let's see here. So the root, I'm just going to rewrite what I had here. The root of 2x squared plus 1 over x all over 3x minus 5 over x, right, becomes, and I guess I should throw my limit out there. I keep telling you guys, oh, you got to put the limit on there, and then I don't do it. Sloppy, sloppy, sloppy. make a little bit of room here. The limit as x goes to negative infinity. So now I'm going to bring this x under the square root by saying, okay, I have the negative root of 2x squared plus 1 over x squared. All over, and I can simplify, right, 3x over x minus 5 over x. If you wanted to just skip to 3 minus 5 over x, that's totally fine. I just want to show you every step, and then there are some steps that you can kind of skip. So if you ended up going straight to this next step that I'm about to do here, that is fine. So I have the negative, make sure you keep that negative, 2x squared over x squared plus, well, you could even skip this step if you wanted to. So much skipping. Over 3 minus 5 over x. I'm kind of babying this, the numerator, because there's a lot going on up there. But if you wanted to go straight to the negative root of 2 plus 1 over x squared, that is totally fine. Over 3 minus 5 over x. And you know what I've done? I dropped the limit again. Bad day for math, I say. I'm gonna have to scoot it in here. The limit as x goes to negative infinity. It needs to be there, but don't be sloppy like me. Because otherwise, if I don't have the limit, then these things aren't going to go to 0, right? And so I'm not going to be able to evaluate this. So I need to be taking the limit, otherwise things won't go away. So now if I take the limit, this is going to go to 0, and this is going to go to 0, right? Anything over x is going to go to 0 as long as it's a constant over x. Things are going to 0 out, and so you've got negative root 2 over 3 is your horizontal asymptote to the negative direction, or in the negative direction. This is the horizontal asymptote as x is going to negative infinity. Right? So it's got this kind of positive negative situation. So that much we know about the look of this thing. The question also asks for vertical asymptotes. I don't want to do the limit because we've got bigger fish to fry today, but I will show you kind of what you would do, and then you would do it just like we've been finding other limits. So let's see here. To find vertical asymptotes, and I think I even stated last day that we would focus on the horizontal asymptotes, right? Because that's this section. And then just a little reminder on vertical asymptotes. Vertical asymptotes, if there are any, they usually happen, or they will happen at spots in that are excluded from the domain. So to find vertical asymptotes, we look at, okay, how do things behave around areas that aren't in the domain? So to find vertical asymptotes, we consider the limits around values of x that are not in the domain. Right, and so kind of Where is this function undefined, right? There, we're likely to see this kind of vertical asymptote situation, limits going to infinity, right? So the difference between infinite limits, which is where x goes to infinity, or limits, or infinite limits. I don't remember what I said. Right? So then we have vertical asymptotes. Okay, so if we consider, right, so f of x we had was the root of 2x squared plus 1 over 3x minus 5. Yeah. So we think about our domain, and well, 2x squared plus 1 has to be positive, right? Greater than or equal to 0. But also, so that's kind of like a blanket restriction, but also we can't divide by 0. So this is the one that we're interested in because it's going to be at a point, right? And so 2x squared plus 1, well, it has to be greater than or equal to 0. 2x squared is always going to be positive, right? And so there's no harm here. 2 times a positive plus 1 is always going to be positive. So there's no restrictions on the domain here, right? So here, since x squared is greater than or equal to 0, we know that 2x squared plus 1 is also greater than or equal to 0. In fact, it'll be greater than or equal to 1, but let's just stick to greater than or equal to 0, right? So there's no restrictions on the numerator. Therefore, no restrictions from the numerator. Oops. Okay. So then I'm going to look at, well, then I need to make sure that 3x minus 5 is not equal to 0. Make sure 3x minus 5 does not equal 0. Okay. So then 3x can't be equal to 5, so x can't be equal to 5 over 3. So what we'll know here is that if there is a vertical asymptote, it would happen at x equals 5 over 3. Okay. So if there is a vertical asymptote, it would likely happen, or it would happen at x equals 5 over 3. So then what do you have to do? You have to take the limit as x is going to 5 over 3 from the left, and then take the limit as x is going to 5 over 3 from the right. I know the direction because I have it here, but right, so we would find, so I'm just going to give it to you, we're not going to do it. Like I said, bigger fish to fry. So we would find that the limit as x goes to 5 over 3 from the left of f of x, I'm just going to shorthand here, is negative infinity, right? So it's kind of dropping down at 5 over 3. And the limit as x goes to 5 over 3 from the right of f of x turns out to be positive infinity. Hey, that doesn't look anything like infinity. Ah, nice. Which you can check all this in Desmos, right? So all these limits you can check. I will say that sometimes it's hard to see stuff in Desmos, right? And so let's just check it out. Where is it? Don't you wish we were dealing with these types of functions? Cute. X squared, x plus 1. All right. The root of 2x squared plus 1. Okay, looks like that. But then it's being divided by, oh, not just the 1, is it? I want to put brackets around here so that I'm dividing everything by 3x plus 5. Okay. So sure enough, right, it's hard to see these horizontal asymptotes that we found, right? Root 2 over 3 and negative root 2 over 3. In fact, kind of really hard because it's a weird number, right? But also we see this positive infinity behavior and negative infinity behavior. So we see all these asymptotes. We just need to be able to calculate them, right? And if you wanted to check, you could say y equals root 2 over 3. Oops, but not in, put the root 2 in brackets here, over 3. And then it kind of, it'll put a line at y equals root 2 over 3. And then if you kind of squint, you can see that it's approaching that root 2 over 3 from the bottom. It doesn't matter where it's coming from, right? They're all horizontal asymptotes, but so you can check that just to make sure that it looks reasonable. But anyways, like I said, it's kind of hard to see exactly what the asymptote is because you'd have to go to infinity, right? Okay, great. So we've dealt with the hardest kind of limit at infinity, which is the rational function, which we divide things out and then things go to 0 and everything is fine, right? But sometimes we're not gonna have a fraction, right? We're not gonna have rational functions all the time as x goes to infinity. So then we need to know, okay, how do we deal with this thing? So I'll just say that's the end of that problem, I guess. It can sometimes be hard to see, right? Or be difficult to see. It can sometimes be difficult to see how a function will behave as x is going to plus or minus infinity, right? And especially if you don't have a rational function, we don't have any tools for dealing with that yet. Okay? So it can sometimes be difficult to see how a function will behave as x goes to plus minus infinity. Right? And so I'm actually going to grab example 10, which is the last one on that handout. But it's actually the easiest one to kind of illustrate what I'm saying here. So if you want to find the limit as x goes to infinity of x squared minus x, well, so x squared is going to infinity, that's infinity. And then minus infinity, I don't know where that puts me, right? Because infinity is not really a number. And so I've got this really large number minus a large number. And it's just kind of hard to, well, we can't do anything here, right? And so what we need to do is we need to rearrange this into something where we can argue that, okay, it is going to infinity if x is going to positive infinite in this case, right? And so here we have basically a large number. I'll do it all caps here, large number minus a large number, right? And so we can't really see what this limit is going to, right? And so we can rewrite the function we can rewrite the function, right, by factoring out an x, right? And then we'll be able to see and argue that, okay, it does go to infinity, which we suspect, right? X squared minus x, okay, I think it goes to infinity, right? And so what we do is we're going to take the limit as x goes to infinity of x times x minus 1, right? And so now it's obvious that infinity times infinity does in fact go to infinity. Infinity minus 1, let's just call it infinity, right? So now it's obvious that it's going to go to infinity, right? Whereas here, when you're subtracting, you're kind of, we don't know what's going on here. So this is going to go to, right, this is going to go to infinity, and then this is going to go to essentially infinity, infinity. And so now we see that the limit as x goes to infinity of x times x minus 1 is just going to be positive infinity, right? Because x is going to positive infinity. Which, just as a reminder, if it's going to infinity, the limit doesn't exist. It's just a special way of not existing. So let's do another one where the behavior is kind of tricky to pinpoint. So we've got example 5. Okay. So here we're letting x go to positive infinity, and I've got the root of infinity squared plus 1, okay, basically infinity, and then minus basically infinity here. And so again, I can't argue that the limit would be anything in particular, right? And so again, I need to rework this until I have something solid, like, well, infinity times infinity must be infinity, right? Something like that. So again, difficult to pinpoint the behavior as x goes to infinity. Oops. If I have a root plus minus some number, or some number plus minus some root, what I want your initial kind of go-to solution to be is to rationalize, right? And so, okay, well, I can rejig this thing by rationalizing and see what happens. In this case, it makes it a little bit more complicated, but it will help to kind of get the ball rolling, okay? And so we have a root, right? So rationalizing is my first stop. So I will try rationalizing this thing. Rationalizing first to rewrite the function. Okay. So what I have is I have the limit as x goes to infinity of the root of x squared plus 1 minus x becomes, and I'm going to move this over here, becomes the limit as x goes to infinity of the root of x squared plus 1 minus x times, do it in a different color. To rationalize, I'd have to do the root of x squared plus 1 plus x over the root of x squared plus 1 plus x, right? I need to multiply by 1, otherwise I'm doing it wrong. So I have the root of x squared plus 1 plus x over the root of x squared plus 1 plus x. And so I know you might be hesitant because it really does make it look a little bit uglier than when we started, but it will work out eventually. Okay. So when we rationalize, right, the reason we do it is because we square the square root, right, and then we get x squared or minus x squared, and everything else cancels out. So this becomes the limit, and you can expand it out by hand. Usually that's what I end up doing. In this case, I've already done it, so I'm convinced. So here, this becomes x squared plus 1 minus x squared over the root of x squared plus 1 plus x. All right, once I expand that all out. And maybe what I'll do is I'm going to underline rationalizing and just kind of put an arrow there to show that that's what I'm doing. Hindsight. Okay. So now I see something really fun happening here. Okay, x squared plus 1 minus x squared. That just leaves me with 1, right? And then I have 1 over a bunch of x's going to infinity. Well, I know how that behaves, right? 1 over x going to infinity is going to zero out, right? And so we find that this becomes the limit as x goes to infinity of 1 over the root of x squared plus 1 plus x. Okay. And so here, this behaves like, I'll do in quotes, kind of 1 over x, right? Doesn't really matter what's going on there, but I think we can all agree that as x goes to infinity, this whole thing is going to go to infinity, right? So my limit then is just going to be 0 as x goes to infinity. So as soon as I'm able to show that, okay, I've got a constant divided by x, and x is going to infinity, I know my limit is going to be 0. Nice. So same kind of toolkit that we've been using, right? Except with the addition of dividing by the highest power of x in the denominator, right? And then otherwise we factored, we kind of rearranged by factoring. That's our first stop. And then if we've got a square root, we can try rationalizing. Often that'll help. So same kind of toolkit that we have been using, right? But always kind of aiming for a 1 over x situation, or 1 over x in quotes. The last example I want to show you guys is sometimes it's going to be kind of a multi-step process, right? And so if we have two functions, kind of one function inside the other function, it might be easier to consider them kind of broken apart and use temporary substitutions. Okay. So that's the end of that example. We will sometimes find temporary substitutions useful. Okay. especially if you see kind of a function inside another function, right? So especially if you recognize a function inside another function. If you recognize a function inside another function. So let's see here. Last example here. Make this bigger here because it's x going to 0 from the left, right? So we're approaching 0 from the left of e to the 1 over x. Now, if we have these split up, right, I know what e to the x looks like, and I know what 1 over x looks like, right? So that's what I mean when I recognize these functions and I know how they behave individually, right? Then I might be able to leverage that by using some temporary substitution. So here, right, we know how e to the x behaves, right? E to the x looks like this, and this is where it becomes really useful to remember what these functions look like, right? E to the x looks like this. Passing through 0, 1. We're not going to use that fact now, but later we will. So may as well throw it on there. And that's here. But we also know what 1 over x looks like. Right? And we know how 1 over x behaves. Oops, behaves, right? 1 over x looks like this. Oh, I'll use a different color. Not very pretty, but that's what it looks like. Ish. So, okay, we've got 1 over x inside e to the x. And so the x that's kind of activated, let's think, is the 1 over x as x is going to 0 from the left, right? So what I can say is that, well, that I know how 1 over x behaves as x is going to 0 from the left. It's going to negative infinity, right? And so here, it's going to negative infinity, right? Okay, so since we know, okay, and so it does assume that we know some of these core functions and how they behave, right? 1 over x, e to the x, logs, polynomials, that kind of fun stuff, trig functions. So since we know that the limit as x goes to 0 from the left of 1 over x equals negative infinity, we make the substitution that, okay, well, I'm going to just replace 1 over x with t, let's say. Usually we'll start our substitutions with t. You could call it y, or you could call it whatever you want. But often if we need kind of a secondary variable, we'll use t. So we can let t be 1 over x. Okay. So then when I rewrite, right, so we can substitute, right, substitute t equals 1 over x into the limit as x goes to 0 from the left of e to the 1 over x. Which means we need to figure out, okay, we already actually know it. What's the limit as x goes to 0 from the left? Well, now if I'm talking about t, which is 1 over x, I know that it's going to be going to negative infinity. Okay, so a little bit weird. Okay. So what we do is we say, okay, I'll start from the top here. The limit as x goes to 0 from the left of e to the 1 over x, I can rewrite as the limit as t goes to negative infinity of e to the t. All right? Because here, okay, as x goes to 0 from the left, we know that 1 over x is going to negative infinity. So now I'm going to let this replacement, right, t, because I know how e to the something behaves, right? I know it looks like this, but also I know as x goes to negative infinity, it turns out that's what we're interested in, is going to go to 0. Which I think we talked about last day as well, right? It was one of those kind of common limits. E to the negative infinity is going to go to 0. And that's because of this graph, right? We have this horizontal asymptote at 0. Okay. So here, right after the substitution, this becomes 0. Kind of wild, but it depends on that kind of substitution of letting t be 1 over x, seeing how t behaves at the original limit, x going to 0 from the left, and then making the adjustments to the original limit, but then it's easy to see. I know, I shouldn't say easy, it's not easy to see. But that's another kind of trick to have up your sleeve. Nothing crazy. Most of the time, we're just going to be dividing by the highest power in the denominator because we'll have rational functions, right? Most of the time. Okay, so maybe we'll do a little break. It's kind of a weird cutoff time. Let's have a break till 10:55. Because then we'll start the next section. Break until 10:55. Struggling with times. Okay, pause. Let's keep going. Sometimes it's nice to have a break though. Just a little,
Gets the brain in from redlining itself.
Oh, say that again?
Keeps the brain from redlining itself.
Totally. I know, we'll see if I'm able to speak a little bit better now. Probably not. Yeah, no guarantees, I think. Okay, I'll start a fresh page here. So section 2.7 and 2.8 are basically the same, except so in section 2.7, this is when we finally start talking about derivatives, which is kind of the focus of this course. But we had to develop all these limits and all that fun stuff before we can talk about derivatives, but the course is focused on derivatives, and then Calc 2, you're focused on integrals. So, which is kind of the opposite, moving in the opposite direction. What's nice about derivatives is that, or nice and not nice at the same time, is that we're going to have all these rules for, and just kind of methods for dealing with different types of functions, right? So finding the derivative. But first, we need to spend a little bit of time talking about what is the derivative, why do we need it, that kind of stuff. And so, and it kind of depends on your field too. If you're going into biology, it's going to be something different than in physics, for example. But the derivative is the derivative, and so that's what this course is all about. So here we go. Kind of enough talking. Derivatives. Derivatives. There. And rates of change. We actually started the section, or the chapter rather. We started the chapter and we said, okay, well, how about if we have to estimate the slope of the tangent line, right? And so we started in chapter 2 and we tried to figure out some methods for finding the slope of the tangent line. So now that we have more limits under our belts, right, we're going to use limits instead to find the slope of the tangent line. Because ultimately the derivative is the slope of the tangent line, okay, at some point. And so, like I said, in 2.7, we're going to look at a specific point A. And then in 2.8, we say, well, we can actually plug in any value of A, making this a function, right? And so then we look at any value of X for our derivative. But the whole goal here is to find the slope of the tangent line at some point. Okay? So I'm just kind of do that little rant here. In chapter 2, or in, I'll say section 2.1, we estimated the slope of the tangent line, right? So we estimated the slope of the tangent line at x equals a. Okay. So in this section, we're gonna name the slope of the tangent line. The slope of the tangent line is the derivative. Okay. So here, this is what's really important. The derivative is the slope of the tangent line. The slope of the tangent line at x equals a in this section, and then later we'll just change it at some value of x. So let's just say at x equals a for now. We can also say that, okay, we called it two different things, right? So we looked at a general example where we said, okay, find the slope of the tangent line. And then we had that ball dropping from the CN tower. We're going to do the exact same problem again, but just using limits instead. And so in that case, we call it the instantaneous rate of change, which is also true for the slope of the tangent line, right? At this exact point, this is how fast things are changing on this function, right? And so I'm gonna highlight this. I don't know how to make it, oh, that's a little dark, isn't it? How do I make it less dark? Maybe orange. We can also say the derivative is the instantaneous rate of change at x equals a. So is the instantaneous rate of change at x equals a. And I'll just highlight that. Okay, so whenever you see the slope of the tangent line or the instantaneous rate of change, you're going to think derivative. And when you hear derivative, you're going to think, okay, it's the slope of the tangent line, which is the same as the instantaneous rate of change, right? So I want you to kind of ball all those things up into one thing and just be kind of fluent moving between them. And that's going to serve you really well, especially when we're solving these problems. And you're going to get to a point where you say, oh, I need to find the slope of the tangent line. Oh, I need to find the derivative. Right. So looking at the handout for 2.7, I have a lot of kind of words in there, but this is the summary of that. So I'm kind of going off script a little bit to try to condense it, but it's okay. So, all right, the slope of the tangent line, what we arrived at before, and I'm not going to bring in these definitions here, okay? So I'm not going to bring in these guys until here. So I'll start here at the slope of the tangent line, but how we got to, so M, remember we used to denote the slope, right? So what happens is the slope of the tangent line at some point A, right? So at some point A is going to be the limit as h goes to 0 of f of a plus h minus f of a over h. This should look quite familiar, right? It's the difference quotient, which we make you calculate in pre-calc, and we make you calculate at the beginning of the term, and it's because we're going to use it as part of the limit definition of the derivative, which is all of Calc 1. Don't worry, come chapter 3, you won't need to do any limits anymore. Then we'll have kind of easier ways of finding the derivative. But I can guarantee you on the final exam, you will need to use the limit definition of the derivative to find the derivative. So we need to do it, but we will have easier ways of finding derivatives later. Okay. So really what's going on, and this is just to kind of talk you through what's going on here, is that if you have a function f of x, right, at some point a f of a, right, so here we've got a little graph. So as we're getting closer to a, right, what we said was, well, we're just going to pick a point that's close to it, and then we estimate the slope as we get closer and closer. That's how we started this chapter, right? And so now we're saying, okay, well, that's the same as letting the limit of x go to a, right? X is going to be approaching a of f of x minus the function at a over, so basically rise over run, right? F of x minus f of a over x minus a. Then, speaking of substitutions, then we say, okay, well, what if we let h be x minus a, right? So h is going to take the role of x minus a, basically the run. Then if you kind of rework this, right, x would become, so if h is x minus a, then rearranging x would be a plus h, right? And so if I take the limit as x approaches a of f of x, but x is now a plus h, right? That's how I get to f of a plus h up here. F of a has nothing to do with x, so it doesn't care, right? And then over h instead of x minus a, right? So really I'm just letting the run be h and rewording it, okay? Then if x is going to a, right, then x minus a is going to 0. So that's where we get this limit from. So the slope of the tangent line, the limit as h goes to 0 because x is going to a and h is x minus a, of f of a plus h minus f of a over h. Don't worry, I'm just talking you through it. It's not something that you need to be able to develop, but we do need to use this definition. Say that again.
I'll be really with you. I'm not certain I retained much of any of that.
It's okay. You don't need to.
Okay, good.
Yeah, don't worry. I had to say it, but now that it's said, we can forget about it. Yeah. Good deal. So, because this is what we're going to be using. Okay. So, what I want you to do is just kind of remember from 2.1, we said, okay, well, I can find the slope of the tangent line, or I can use the same methods to find the velocity at some point A, right? And so notice that these two are the same, right? Without using them yet, we see immediately that, okay, the slope of the tangent line and the velocity given some distance function, they behave the same way, right? And so, okay, we can use that. And then let's scroll ahead a little bit, because here's the first time that we see the derivative of a function, right? So we'll do these examples, of course, so don't worry, but I just want you to see the links here. The derivative, which we'll talk about, right, is the limit as h goes to 0 of f of a plus h minus f of a over h, which makes sense. We said, okay, we've established the derivative is the slope of the tangent line. Well, the slope of the tangent line is this limit, right? And so we're going to build off of this. And while I have you on the line, so to speak, why don't we go to just 2.8? And all that's changing in 2.8, I know. What a way to start your Friday or end your Friday, depending on what's going on. All that's changing in 2.8 is the line, yeah, just some music. So the only thing that's changing here, right, is that now I'm taking the derivative at any x, okay? But the limit as h goes to 0 of f of x plus h minus f of x over h should look quite familiar from 2.7. So in 2.7, we're looking at a specific point A, and in 2.8, we're saying, hey, we could actually plug in any value of x here that we wanted to. And then we just do the whole thing over again. So I'm parking lotting. I like to say parking lot, but I'm parking lotting 2.8 for next day. But just so you see that there's really nothing crazy happening between 2.7 and 2.8. So like I said, what you need to kind of have from this section is this relationship here, okay? So let's bring it in here. Whoops. Okay. And here is the slope of the tangent line at A. Okay. So we'll use this definition first. And then we'll do a velocity problem, and then we'll do call it the derivative. But knowing that the derivative is the slope of the tangent line, well, we're already doing derivatives, right? But we're not calling them that yet. Okay. So let's see here. I want to do this example. And I'm sure we did something similar, right? But it was probably a lot more work than what we're about to do. So find an equation of the tangent line, right? So not just the slope of the tangent line, but the equation of the tangent line of y equals 3 over x at the point 3, 1. Okay? So what we need to remember, and what's going to be really, really useful, I've said it once, I'll say it again, is, okay, the equation of a line, right? We can use the point slope form of the line if we have the slope, derivative, and we have a point, 3, 1, right? So really what we're saying is we need to find the derivative at 3, 1, right? So we need to find the slope of the tangent line at 3, 1. So remember, oops, that should say remember, not really, that's okay. To find the equation of a tangent line, or to find the equation of any line, but I'll say in brackets tangent line, because usually that's what we're interested in this course, right? So remember I said, okay, this course is about derivatives. The derivative is the slope of the tangent line. So of course, a real focus is going to be equations of the tangent line. What's the slope of the tangent line, right? We're going to talk about the tangent line a lot. So to find the equation of a line in general, but definitely the tangent line, we first need to find the slope. We need to find the slope, which of course is m. Then we use the point slope form of a line. Right? Then we use the point slope form of a line given a point x naught, y naught. And I'll keep it on the same page here. In fact, I'm just going to bump this up just a smidge because I just need one more line. One more line. There. So the point slope form of a line says that, okay, you can construct a line given a point and the slope, of course, by taking y minus y naught is equal to m times x minus x naught, right? Where x naught is the x that you know, y naught is the y that you know. Right? Thinking about the information that we have already, x naught is 3 and y naught is 1. So we already have a lot of the components, right? But we need to know what m is, right? So I'm gonna just put a little highlight around there because that's gonna be really important to remember, kind of have up your sleeve. And if you're making like a cheat sheet along the way, I'm not calling it a cheat sheet, but you know what I mean. Right, so some sort of summary as you go, then having the point slope form of a line on that sheet would be a really good idea. Right. So, all right. So we already know x naught, y naught, it's 3, 1. That's the point that we're interested in, right? And so I could start here. Okay. So we know But x naught, y naught in this case is going to be 3, 1. Okay. So I can substitute those in to see what I need to find next. So y minus, and I should do the bare bones formula first, m times x minus x naught. Y minus 1 is m times x minus 3. Okay. Here, we need to find m at 3, 1. Okay. What I'll take away from this is at x equals 3, right? Because we said, okay, we want to have a specific value of a, and in this case, x equals a is 3. At 3, 1, so at a or x equals a equals 3 from here. Just want to show you all the linkages. Okay, so we can use that that formula or the definition that we had earlier. Okay, let's see here. 3 over x is our function. And we need to use this limit to find the slope at a, which happens to be 3 in this case. So m is the limit as h goes to 0 of f of a plus h. So just going to do the general version minus f of a over h. Okay. And then here I'll put on the side, recall that y equals f of x equals 3 over x. Right? Making sure that you have that connection in your mind that, okay, when I see y, it's f of x because y is a function of x. But also when you see f of x, you can just simplify it in your mind as y, right? So depending on the situation, you can move back and forth there. But because we need a function here, may as well write it as a function. So then we say, okay, well, from the point, right, a equals 3, I can put into this function here, right, or this limit. So to find the slope, I'm going to find the limit as h goes to 0 of f of 3 plus h minus f of 3 over h. And remember, we're just letting h go to 0. And when we worked with these functions before without being limits, we did find that this h usually cancels out, right? So we need to rework this thing until this h cancels out and then take the limit as h goes to 0. So, okay, I get the limit as h goes to 0. F of 3 plus h is 3 over 3 plus h. 3 over 3 plus h. I'll put big square brackets around it just to keep them separate. Minus f of 3. F of 3 is just 3 over 3. Again, I'll put big brackets around them, but you don't have to. All over h. There's a little bit of work here, but compared to what we were doing in the previous section, dealing with fractions and finding common denominators is kind of child's play here, right? So it might be easiest to simplify 3 over 3 to 1 and then multiply by 3 plus h over 3 plus h to get that common denominator. So let's do that. I'm taking the limit as h goes to 0 of 3 over 3 plus h minus 1. And then I'll just show in a different color times 3 plus h over 3 plus h over h. Because it's been a while since we forced the common denominator, that's why I'm doing the different color. And I just find that it helps me see, okay, this is a new thing that I'm introducing. So you don't have to, but you do have to have a common denominator. So the limit as h goes to 0 of 3 minus h. Be really careful here. In this case, it was a simple kind of expansion, right? -1 times 3, -1 times h. If this was a bigger function, I would probably do it in multiple steps, right? Not try to bring in the negative at the same time. So just that's a side note to be careful, but over 3 plus h all over h. Okay. So now I'm going to find the limit as h goes to 0. 3 minus 3 goes away, -h over 3 plus h. And then remember, if I have a fraction over a fraction, I have to flip the denominator and multiply, right? So really, when you look at h in the denominator, it's really h over 1. So h over 1 becomes times 1 over h. Notice that this h and this h are going to cancel out to 1. So now I have the limit as h goes to 0. You don't have to write it out again, but I just like to see it nice and clean. -1 over 3 plus h. Now, when I let h go to 0, I'm not dividing by 0 anymore. And so now I can say, okay, well, then my slope, which is where we started, here. The slope at 3, x equals 3 or 3, 1, right, is going to be -1 over 3. Right? So m, therefore m is -1 over 3 at 3, 1. Nice. So like I said, all you need to be able to do is use those definitions for the slope and the velocity, and then eventually the derivative. You don't need to know how we kind of got there. Okay. So now that I have my slope, right now, oh, so laggy today. Now I can plug that in and find the equation of the tangent line at 3, 1, which is what we wanted to do. So I'm going to copy this because I'll never remember. I shouldn't say never. So we can now let m be -1 over 3. So y minus 1 is -1 over 3 times x minus 3. Have all the components of finding the equation of the line, which happens to be the tangent line. And so I get y is -1 over 3x plus 3 over 3 plus 1. Hopefully I did that right. I did. Which y is going to be -1 over 3x. Makes sense, right, that this wouldn't change, right? The slope is the one that's attached to the x. So you just want to kind of check yourself, make sure that that's actually what's going on. 3 over 3 is 1 plus 1 is plus 2. So one thing that I wanted to highlight was if we look at, so we had this example here, and then I've actually got the graph of it here. but it looks a little bit different. So we found that this is the equation of the tangent line, that it is, right? Notice that they've written it a little bit differently here, right? And so, but this is what 3 over x looks like. This is at 3, 1. And so this is the equation of the line that we found, right? And so we can rewrite this to match to match the figure, right? Well, all you'd have to do is move everything over and set it equal to 0 instead, right? So, but just to kind of convince yourself that, oh, okay, nothing weird is going on here. So then we have y equals negative 1 over 3x plus 2. So y minus 2 is negative 1 over 3x. Slowly moving things over. I can multiply by negative 3 to move that negative 1 over 3x over. So then I have negative 3y plus 6 equals x. Moving that x over, I get negative 3y Oh, looks like they moved it to the other side. That's fine.
Probably would have been easier just to shift everything over so that it was all equal to x, then multiply 3 by both sides. But
yeah. Either way, as long as you're able to kind of convince yourself that this is the same as this, I'm happy. Right? So just so you're not kind of caught off guard and saying, oh, well, this looks way different. It does look way different, but it is the same. Right? So I'm just going to try to match this by moving all these things over to the right instead. So then 0 equals x plus 3y minus 6, which is what they have. Good. Right, and so we know that the velocity behaves the same as the slope of the tangent line. And so it's the end of that one. From section 2.1, we also know the velocity of an object, right? And I'll say given the distance function, right, or the displacement, given the, and now I'm hesitating, is it the distance or displacement? They're different, right? But I'll say distance. Given the distance function, usually has something to do with gravity, right? Throw a ball up and it goes up and then it goes down. So if we know how it behaves in the distance function, we can use that to find the velocity of the object at some time. So we also know the velocity of an object at time t equals a is equal to the slope of the tangent line, is equal to the slope of the tangent line. So I'll grab that little definition here. Maybe get it here. So we've said that the velocity at some time point A, well, it behaves the exact same way as what we were just doing, right? So we need to know the function of the distance, right? Which was a little bit tricky in 2.1, right? But now we've seen that distance function, and so we're just going to use it again. And I think I even have it in the side, yeah. Sidebar here. Just throw it in on the same page here. So the distance in meters fallen after t seconds is 4.9 t squared. Okay. So that would be our distance function. And then when we take the derivative of that eventually, right, we'll have the velocity. So let's see here. We've got a problem to do. This one. So again, we're letting a ball drop from the top of the CN tower, which is 450 meters above the ground. Again, we want to find the velocity of the ball after 5 seconds, and then how fast is the ball traveling when it hits the ground. We've already solved these problems, right, but not using limits. And so now we're just re-solving these problems using limits. And I'm sure we'll come back and do these, if I have anything to say about it, when we have easier ways of finding the derivative as well, right? And we'll just kind of rework these with more efficient solutions every time. So, okay. We know that S of t, which is the distance, is 4.9 t squared, right? And that's just from here. I gave it to you in the sidebar. And so what I'm going to do, instead of talking about S of t, because we actually have the velocity in terms of f, so I'm going to replace s and f. It doesn't do anything, but otherwise this would be s of a plus h minus s of a. Doesn't matter, but we will rewrite s of t as f of t to match definition 3. So then f of t is 4.9 t squared. Changing the name of the function doesn't actually change anything. So now we know that v of t, the velocity at time t, so any time point t, is going to be t plus h. So f of t plus h minus f of t over h, the limit as h goes to 0. So the v of t is the limit as h goes to 0 of f of t plus h minus f of t over h. Noticing that I'm just developing a function for the velocity in terms of time, right? Any time point t. So we're actually already doing what we're going to be doing in 2.8, right? And so just kind of, we've already done it, but it's going to feel weird in the beginning. All right, so we're developing this general velocity function, and so let's do it. I know that f of t is 4.9 t squared. So then what gets weird here is that I have a t here and I have a t here. We need to keep those separate, right? So I need to plug in t plus h in for t here. So this becomes the limit as h goes to 0 of 4.9 times t plus h squared minus 4.9 t squared over h. looks reasonable enough, right? We've dealt enough with these difference quotients to know that, okay, once I expand this out, things are going to cancel, and then I'm going to be able to cancel an h, and everything's going to be fine, right? And so they are a lot of work, but it's just tedious. It's not hard, right? So we need to expand this out, and then we know that it shrinks down. So this is going to be the limit as h goes to 0 of, I'll keep it in big square brackets just to kind of block them off, but 4.9 times t plus h times t plus h. I always like to emphasize to myself that t plus h squared is t plus h times t plus h, and then I do the expansion every time, minus 4.9 t squared over h. Once I do the expansion, I get to the limit as h goes to 0 of 4.9 times t squared plus 2th plus h squared minus 4.9 t squared over h. Shaping up already. Need to expand that 4.9 inside, but I can already see that it's going to cancel out with this minus 4.9 t squared. And then I see the light at the end of the tunnel because I'll be able to factor out an h and cancel with this h in the denominator. Right, so we're almost there. The limit as h goes to 0 of 4.9 t squared plus 4.9 times 2 is 9.8. th plus 4.9h squared minus 4.9 t squared over h. So then, 4.9 t squared minus 4.9 t squared is going to cancel out. And I'll be able to pull out a common h. The limit as h goes to 0 of h times 9.8t plus 4.9h over h. Just highlight that those cancel. Now if I let h go to 0, I'm finding that the velocity at any time point t is going to be 9.8 t. This is the velocity at any time t. So we wanted to find, okay, so now we can go back and we can say, let it catch up. What's the velocity of the ball after 5 seconds? So what's the velocity at t equals 5? So we haven't even started the problem yet, but now we have all this information under our belts. So A, we want to find the velocity at t equals 5. Well, v of 5 is 9.8 times 5, which is going to be 49, and really I'm only concerned with units if it's physics, and we'll talk more about units next day, but right, and so the distance is in meters, the velocity is in meters per second, the acceleration we'll find as meters per second squared, right? So it helps if you've taken some physics, but you don't have to. And the derivatives actually help us remember what the units are, but that's for next day. So at 5 seconds, the velocity is 49 meters per second. All right. So the last part, or I guess the second part, how fast is the ball traveling when it hits the ground? So we have our velocity function. But now we need to know, okay, well, how long until it hits the ground, right? How long until it's traveled 450 meters? Okay. So I'll just summarize here the velocity when it hits the ground, question mark. Right. Means that we need to find when it hits the ground. Need to find t when it hits the ground. Which is after 450 meters, right? We were told that in the initial blurb. So it has to fall a distance of 450 meters, and we need to figure out how long that takes. So luckily, right, 450 meters is a distance. And so we know S of t is 4.9 t squared. We also know the distance has to be 450 meters. So 450 meters has to be 4.9 t squared. Now I can solve for t after 450 meters, which happens to be the ground. So 450 divided by 4.9 becomes t squared. So t, I do this switcheroo all the time. I'm not sure we've done enough of these kind of solve for x problems to have seen it, but I always like to have what I'm solving for on the left. So I just use the fact that an equal sign is an equal sign. I just swing them around. So then, but I'll also usually do a manipulation in the swing around. So it's the square root, but remember when I take the square root, it has to be the plus and the minus, which we actually already talked about today. 450 over 4.9 is the exact answer. One thing is that, well, the square root is always going to be positive. So when I take the plus minus, I need to remember that time can't be negative, right? And so the negative option is not in the domain, right? So since time can't be negative, t equals negative root 450 over 4.9 is not in the domain. Right, so it can't be one of our options. So that's why we're able to say that, well, then t must be the root of 450 over 4.9. Which I've got it calculated out here, because we'll use a decimal approximation. You could absolutely use the exact value, doesn't really matter, but I shouldn't say it doesn't matter, it matters, but in these circumstances, it doesn't matter. 9.58, just so we have an idea of what this number is. 9.58314, 8475 seconds, because time was in seconds, meters per second, right? So t is roughly 9.58 seconds. When it hits the ground. When it hits the ground. Well, if I know the time and I have the velocity function, right? So v of t was 4.9 t, I want to say. Sorry, 9.8 t. Well, should know that. So then the velocity at 9.58, which is when it hits the ground, is 9.8 times 9.58, which, how come I have 4.9 here? I tried to do that again. Sorry, just checking. In my notes, I have 4.9 times 9.58. That's not right. Okay. Which is going to be 93.884 meters per second. Okay. So what I want to do is let's just leave that for now, and then we'll use the rest of chapter or section 2.7 to introduce 2.8 next day. And then we'll be done with limits for a long time. Any questions before I let you go have a weekend?
I would if I had any brain cells left operational.
It's a big day today. All right, then have a great weekend. Let me know if you have any questions.
Will do.
I'll post some homework for these sections if I haven't already. I'll check. Can't remember.
All right. See you
See ya.
Wednesday.